Welcome back to ECE 501B. Exam number 1 is on Wednesday. I believe that's the 1st of October in 2014. I'm not sure who has checked in the last few minutes, but I decided to go ahead and post a review session lecture. It's only about 30 minutes long from last fall. The material last fall went through some pages of Chapter 5. You will not be responsible for eigenvalues and eigenvectors, although that is the material we will begin with today. We're trying to get ahead so that you can do homework after the exam, because I know you want to do that this weekend. Today, we will quickly review what we had said last time, I believe, on exam number 1's process and structure. Then we will breeze through Chapter 4, meaning we will just state some of the ideas so that they're floating around in our head and we are aware of those. We will use those as we move throughout the course, or the rest of the course, which will take us immediately into Chapter 5, which is dealing with eigenvalues and eigenvectors. And today we'll just try to sort of motivate that or talk about eigenvalues and eigenvectors and what that may mean as far as the existence of eigenvalues. And that really is going to depend on the fields over which we are allowing these matrices to have scalars or to contain elements in. The process, 2 sheets of notes, and that's all the written material that you will need to bring into the exam. I will give you the paper to write on. If you need extra paper, please let me know. Something to write with, hopefully. You won't have to bring something sharp to be writing in anything other than ink or pencil. And a calculator. I'm not sure you will need a calculator, but if you need to add up 1 and 1, the calculator might help you get through that particular stalemate that you might arrive at in your exam. It might be faster than thinking through that process. Everything else is not allowed. No textbook, no classmates, no cell phone, and no computer. The structure, I think, will be similar to last fall's exam. 5 problems, at least 1 proof is what I'm thinking. As you can tell, the exam has not been created yet, but you will need to demonstrate or create and build things related to chapters 1, 2, and 3 in the textbook, similarly or similar to what you've done on the homeworks and what's indicated in the exam. That's what I want to leave you with for exam number 1, which again is Wednesday. Here is our short trip through Chapter 4. We will just extract some of the main theorems or ideas, and we're dealing with polynomials. And if I say an mth order, Michiganth order polynomial, then that's represented here by the lowercase subscripts. If I say a second order, then little m is 2, for example. The roots, here's proposition 4.1. Lambda is a question? So the question is, does that mean that m is always finite? And the answer is no. We can let m just get bigger and bigger. So we don't necessarily restrict our polynomials to be finite dimensional, but most of the time moving forward, that's to be consistent with the textbook. Most of the time now moving forward, we are dealing with finite dimensional vector spaces post Chapter 2, or starting with Chapter 2. So most of the time, yes, little m will be finite, and we'll be dealing with polynomials associated with finite dimensional operators that are square. Yes? So we, yes, we could include, if we were taking some infinite series, we could let m march off to infinity if that's the way we want. But we're dealing with polynomials, and typically that will just be this finite limit on our powers of, in this case, z, and in maybe later cases, x, for the variable that is the argument of our polynomial. In terms of roots, those roots really depend on the field over which we allow our scalars to live within. And f, again, in this class for now will be the real numbers or the complex numbers. Lambda in a field, R or C, is a root of a polynomial p if and only if you can factor out that linear factor z minus lambda. And so you have this smaller polynomial left over, but you can explicitly factor out this value, z minus lambda, which to find a root, you're setting p of z equal to 0, and hopefully you can see then that if that factor factors out, z minus lambda is equal to 0 is a root, so z is equal to lambda. That's if you can factor it out. Now, the fundamental theorem of algebra, which I guess we start algebra in elementary school, and you probably, maybe you don't learn the fundamental theorem of algebra then, but the fundamental theorem of algebra is based on the fact that this field of numbers is complex. With a complex field, every non-constant polynomial with complex coefficients has a root. Meaning once you get up to something other than a constant, z plus alpha, that has a root, where you're allowing z and alpha to range over the complex number field, or the field of complex numbers. That's not true if you restrict the field to be real numbers, which is Theorem 414. In Theorem 414, if the field is real, or the set of real numbers, or the field of real numbers, and c, lambda 1, lambda sub m are real, alpha sub I, beta sub I are also real, and as long as this discriminant is such that alpha sub I squared, and that's this, if you're thinking of the quadratic formula, where you might have the leading coefficient now has been normalized to 1, but a lot of times I remember that as ax squared plus bx plus c. If b squared minus 4 beta 1 is essentially negative, then you're not going to have real roots of that quadratic factor, or those quadratic factors, where I'm assuming now the polynomial has been factored to explicitly include all of the real factors, and the quadratic factors then that cannot be, or that do not possess real roots, are left as quadratics. And that's a possibility when we're restricting attention to real coefficients and real roots. We can't always find, let's say if we had a fourth order polynomial, it may be true that we can only find 2 real roots or no real roots to that fourth order polynomial. That's Theorem 414. So we have to keep track of the field, whether that is real or complex. When it's complex, we have much more freedom or flexibility or opportunity to be finding roots. That's all there is to Chapter 4 that we will cover today, is Proposition 4.1, what do we mean by a root? Theorem 4.7, the fundamental theorem of algebra, where the field is the complex numbers, and then Theorem 414, reminding ourselves that there are cases where we may not be able to find roots of a quadratic that are real. Those quadratic roots might be complex. They may have a non-zero imaginary part, and so we can't go any further than that. And that will then play into this idea that we work with in Chapter 5, which is eigenvalues and eigenvectors. So if we're restricting our attention to real number fields, then we may not have a full set of eigenvalues and eigenvectors for every matrix that we're dealing with. So let's go there and see what that means relative to Chapter 5. And remember, with linear algebra done right, that's the title of our book, determinants are at the very end of the material, Chapter 10. So we're not using determinants or traces to figure out eigenvalues and eigenvectors. We're going to try to build those up on their own and then have determinants at the very end. Eigenvalues and eigenvectors. Now that we've made it through Chapter 3, we're now able to be working with operators. And what were operators as a review for the exam? Or what is a property of an operator? Everybody catch that? I can't hear very well, so I didn't hear that, but we're mapping the domain and the codomain are the same, vector space. We're mapping from one back into itself, and we will be dealing now with matrices that perform that linear transformation, and we could say that now we have this matrix representation from an n space to an n space over a field of numbers. Whether that field is real or complex, we will have to either know or be told. And we now have this linear transformation, which is represented by a matrix A as a square matrix. The concept, so we're really just starting by giving us what we're going to be playing with. We have AX equal to lambda x. That's the eigenvalue eigenvector equation, where all of the elements of A, or the entries in the A matrix, are generically coming from F, either real or complex scalars. The vectors, or the vector x, it's just one vector. We're allowing its coordinates to come from that same field, F, and the scalar, lambda, is an element of F. That's our eigenvalue eigenvector equation. We really haven't done anything. I've just now given it to you. If it just so happens that a vector x and a scalar lambda exist, then x is what we will call an eigenvector. And lambda is an eigenvalue. So that operator A in that equation, ax equal lambda x, the operator takes a vector. Again, that's an n by n matrix or a linear transformation, and actually maps back into a scaled version where the scaling is the eigenvalue lambda. The operator takes a vector and maps back into a scaled version of that same vector. Yes? So now if the question was if lambda is a complex number, then are we really scaling it? There it's, I guess, how we define scaling. We may be stretching and rotating essentially with this complex number. So yes, it depends on how we define scaling. Well, I may just let scaling mean we're changing it in a sense, but yes, so you could think of saying if we do have a complex number, you can think of that written as terms of a magnitude and an angle, so to speak, and now we sort of scale by the magnitude and we rotate by the angle. And if we lump all of those together into a generic scaling, then that's okay to use, or say, then a scaled version of that same vector. So that's a good point. We need to see what's happening with respect to real and imaginary, but a lot of times we simply look at the real parts and look at the imaginary parts, and they both sort of satisfy the underlying relationship or equation. Here, most of the time we'll be thinking in terms of the real number field. So suppose, just so that we can get a conceptual understanding, x is R3, or we're living in this three-dimensional space. Then the operator's action keeps the point in 3D space on the same line as it started. And that's the intuitive thing that we want to sort of keep in mind when we're talking about an eigenvalue or an eigenvector. Now we start at some point, and that point can be used to draw a line through the origin, and now the eigenvector actually keeps us on that line. We map from that point back onto the line. Maybe we've just been relocated somewhere other than where we started on that line. Let's go through some examples so that we all are sort of starting together. Example 1. Suppose A1 is -1, 0, 0, -2, and I hope that everyone starts to say, oh boy, he's starting pretty easy here with this matrix. A1 is a diagonal matrix which is Saturday Night Live still on? Special. This is now a special matrix. It's very special, actually. Or we could say a nice matrix operator. If we look at this matrix operating on some vector. Let's suppose that the vector that we choose, v1, actually lies on the x-axis. And a straightforward vector that's in the x-axis direction, we could just say, let's let v1 be the standard vector 1, 0. If we now take a1 and operate on it with the vector in the x direction, we now have minus 1, 0, 0, minus 2 times 1, 0. What's our output? If we view this x direction as if it was an input, here is our output. If we think in terms of what we were talking about earlier in the class, this input vector is really just pulling off the first column of the two columns in our A1 matrix, which means that we're now just pulling or generating for an output minus 1, 0. But that we can rewrite. We can factor out minus 1. And now this is actually minus 1 times v1, and that's just a scaled version in the x direction. It's now we've just reflected 180 degrees through the origin. But we've stayed on the x-axis. The resulting output vector stays on the x-axis. And the output itself, or that vector, is scaled by minus 1 from the input, which the scaling is 1, the direction has been changed 180 degrees, is sort of a way to think of that. If we look at another vector that is operated on by A1, suppose v sub 2, since we had such good luck with the x direction, let's go in the y direction. If we say, suppose v sub 2 lies on the y-axis, we can now let v sub 2 be 0, 1, and now a1 v sub 2 using our strategy from before, that's just going to pull off the second column in a1, producing 0, minus 2, but that's just minus 2 times v sub 2. Or again, because of the special nature of those vectors, in this case v sub 2, the output vector, because we started on the eigenvector, we remained on that eigenvector through this linear mapping a sub 1. The output vector stays on the y-axis. Now it's scaled by minus 2. So we've gone twice as far from the origin, and we've rotated or turned around by 180 degrees. Yes? So now A1, it depends on the question. I'm not sure I'm understanding the question exactly, but it was important which vectors we started with in our input. We actually were very selective in the vectors that we chose. And we chose the x direction or the y direction, and those just happen to be the eigenvectors for this particular matrix A sub 1. And because we chose those two vectors separately, we were able to show that A1 operating on in that direction maps back into that same direction. The scaling is sort of open for interpretation. -1 is either a scaling of -1 or it's a scaling of 1 with a rotation of 180 degrees. It's really how you want to interpret or define scaling. And -1 happens to be one of the eigenvalues, -2 happens to be the other eigenvalue. And it's not coincidental that we obtained A1 V2 is equal to -2 V2, or V sub 2. So let's make some comments from this example. And these comments are based only on this example, which was A1, which is the diagonal matrix. The initial vectors were eigenvectors. The scaling quantities were eigenvalues. The A matrix itself was made up of real elements, or the elements in the matrix were real, and the matrix was 2 by 2. If we were looking at the dimension, that now has dimension 2, which now allows us to say that we have 2 eigenvalues. We actually had 2 eigenvectors. The scaling values were actually real numbers, and the A that we were using, the matrix, was diagonal, and the eigenvalues were actually right on that diagonal. The diagonal is both upper triangular and lower triangular, and any of those two, upper triangular or lower triangular, the eigenvalues will be on the diagonal. The eigenvalues were the elements on the diagonal. There we were crawling. That was basically 2 sort of scalar problems because of the diagonal nature of the matrix. Question? So the question was, it looks like we have an infinite number of choices for our eigenvectors, and that's true. It's just we need those to be in certain directions. You can pick any vector whose, let's say, endpoint is on the x-axis, and that would be an eigenvector in the proper direction. Similarly to the y direction, it doesn't have to be this 1, 0, 0, 1, but those are normalized, and those will become nice in the sense of those choices for an eigenvector. We may at some point say, let's normalize our eigenvectors, and then it might be that you want to pick a 1, 0 or a 0, 1. But yes, the eigenvector is now any point in that, or any vector in that direction will be an eigenvector. Is that the question? So we could have 2, 0, and that would be an eigenvector. 2 being in the first coordinate and 0 being in the second coordinate for that A1 matrix. And you'll see that that's true in general. If you simply scaled by whatever we haven't used, beta, both sides by beta, you can put that beta and scale your vector V1. So now you have a beta V1 and a beta V1 on both sides, and it still satisfies that eigenvalue eigenvector equation. And beta can be anything, which is, I think, what you were saying. Beta can be an infinite number of values. Example 2. Suppose a sub 2, you can see I'm getting creative with my subscripts and I'm getting really elaborate with my examples. I'm really going quickly, or really moving fast. Now I have a matrix A sub 2, which is in the top row minus 1, 1, and in the bottom row 0, 2. This is an upper triangular matrix, and we can basically make some comments relative to this. We already know for a triangular matrix that the eigenvalues are on the diagonal. So the eigenvalues are minus 1 and minus 2. They're on the diagonal. Lambda 1 is minus 1. What's its eigenvector? Can you pick a vector such that when operated on, used to operate, or when A2 is applied to V1, when will you get lambda sub 1 equal to minus 1 as an eigenvalue? 1, 0, where 1 is our first coordinate and 0 is our second. What about lambda sub 2? Its eigenvalue. Lambda sub 2 is minus 2. Now I've hidden the matrix from us. So maybe I'm not being very fair, and I'm assuming you had that memorized. But now maybe it's not so clear unless you were playing around a little bit with some paper and pencil. But now V sub 2 is not just along the y-axis. This is now going over, let's say, 1 in the x direction and minus 1. This is now this line at a 45-degree angle, a minus 45-degree angle with the horizontal x-axis. And we could verify that if we wanted to. We could have guessed and then verified, which is what we're doing. If we look at A sub 2, V sub 2, A sub 2 was minus 1, 1, 0, minus 2. A sub 2 we said was minus 1, 1, which now says let's scale the first column by minus 1 and add to that the second column. Our result then is 1 plus 1 up in the first coordinate. It's 0 minus 2 in the second coordinate. We now have 2 minus 2, which if we factor a minus 2 out of that, we end up with minus 1, 1, which is the direction. Whoops, I was going in the wrong direction when I was talking about V sub 2. But it's okay. I guess I was just thinking in the same direction. It's now a minus 45 from the horizontal x-axis. Any questions on that example? Let's look at a different matrix. That maybe is not quite as obvious what the eigenvalues are, or if they even exist, if we restrict ourselves to real number fields. Minus 3 halves minus 1/4, minus 1 minus 3 halves for B. And now does B have any real eigenvalues? If we are looking for eigenvalues, we are trying to have those satisfy the eigenvalue eigenvector equation, and so we need bx to equal some scaled version of x. And to check that out, let's just go ahead and let x be some variables, x sub 1 and x sub 2. If we now use that in bx equal to lambda x, we have the following relationship, which gives us two equations. In the top row, we have minus, or from the top row, we have minus 3 halves x1 minus 1/4 x sub 2 equaling lambda x1. And in the bottom row, we have minus x1 minus 3 halves x2 is equal to lambda x sub 2. We now have two equations in these two unknown x1s and x2s, are coordinates of our eigenvector matrix, and we want to see, is there a lambda or are there lambdas that will allow us to satisfy these equations for values of x1 and x2. From the top equation, we can combine the x1 terms, and we have minus 3 halves minus lambda times x1 minus 1/4 x sub 2 equaling 0, and maybe I'll call that equation A. In the bottom equation, we now have minus x1 plus minus 3 halves minus lambda x sub 2 equaling 0, or we can now say x sub 1 is equal to minus 3 halves minus lambda x sub 2. We can use that relationship for x1 to eliminate x1 in equation A. If I now call this equation B, let me substitute B into A. So that now I can eliminate x sub 1, and I have minus 3 halves minus lambda times minus 3 halves minus lambda x sub 2 minus 1/4 x sub 2 is equal to 0. Or we now have minus 3 halves minus lambda squared minus 1/4 times x sub 2 equal to 0. And we want to find, are there values of lambda that will allow this equation to be true? And if there are, then that lambda or those lambdas will be eigenvalues. Is there a lambda, a real lambda, such that square bracketed term is equal to 0? If we can find that, then that expression is actually going to be equal to 0. We could use the quadratic equation or the quadratic formula to find that, or why don't we just set that bracketed term to 0, which really says that we need minus 3 halves minus lambda squared to equal 1/4, adding 1/4 to both sides after setting that equal to 0. We now want to find, are there values of lambda such that when we square the left-hand side we get 1/4? Or does the left-hand side equal 1/2? Or minus 1/2, really? Or we could get that same result by saying, let's take the square root of both sides. We now have minus 3 halves minus lambda equaling plus or minus the square root of 1/4, which is plus or minus 1/2. Now lambda, if we solve for lambda, or adding lambda to both sides and subtracting and adding 1/2 to both sides, we end up with lambda being equal to minus 3/2 plus and minus 1/2. Or we have minus 1.5 plus 1/2, giving us minus 1, minus 1.5, minus 1/2, giving us 2. We now have exactly the same eigenvalues that we had in A1 and A2. It's just now they were sort of buried in this a little less trivial matrix B. But we do have real eigenvalues. Where are the eigenvectors? We now have found two real eigenvalues. They're distinct, -1 and -2. The eigenvectors are these values of x1, x sub 1, and x sub 2 that satisfy this relationship, bx equal lambda x. And we've already found some expressions that allow us to maybe deal with x1s and x2s. So if we look at the first equation, minus 3/2 minus lambda x1 minus 1/4 x2, let's start with that. That needs to be true for x1 and x2. Or we also have minus x1 plus minus 3/2 minus lambda x sub 2 equals 0. Those were our two equations. We can now put that into a matrix structure. If you like to think in terms of matrices, we have minus 3/2 minus lambda minus 1/4. We have minus 1 minus 3/2 minus lambda times x1, the vector x, which is x sub 1, x sub 2, equaling 0. And what kind of an equation is that, or what does that say about this vector x? The matrix that is pre-multiplying x is actually our original matrix B with lambda taken away from the diagonal. That's just B minus lambda I. X, can you tell me anything about x and maybe a space it might live in? It's in the null space, isn't it? We now have a vector x that's living in the null space of some vector or a matrix B minus lambda I. X is in the null space. Or we could say x is an element of the null space of B minus lambda I. But we now know two values of lambda that satisfied those equations, and let's now use those specific values of lambda to find the x's that satisfy this equation. With lambda 1 equal to minus 1, now we have, in terms of a matrix, we have minus 3/2 minus 1, or that's now minus 3/2 plus 1, or minus 1/2, minus 1/4, minus 1, and we have minus 3/2 again, minus a minus 1, or minus 1/2. That's now x1, x2. And what can you tell me about those two columns? Or do those two columns have anything in common? They are in the same direction, aren't they? Or they're dependent. And that, pardon? Yes, they both are in the span of the other one, aren't they? So we can now find a linear combination of one to give us the other. Those are dependent vectors, and that's what we need if we have a non-trivial null space. We need some dependence among our columns or rows in our matrix in order to find a non-zero vector in the null space of that matrix. These columns are dependent, which we need to find a non-trivial solution to this equation. The columns are dependent. Which now says that we have a null space that's non-trivial. Or we can now just let x1 be some number. Let's let it be something nice. x1 equal to 1. And now from the top, or which one do we want to use? Let's go ahead and just use the bottom, since it's easier maybe to see. We now have minus 1 minus 1/2 x sub 2 equaling 0. If we multiply both sides by 2, solve for x sub 2, we get minus 2 is equal to x sub 2. Or now the eigenvector, an eigenvector associated with the eigenvalue minus 1, has the top coordinate of 1 and the bottom coordinate of minus 2. We've now found an eigenvector associated with one of the eigenvalues. This eigenvector is now, if this is now going to satisfy b x bar equal what? Lambda x bar, where lambda is, remind me, minus 1. This is now the direction which, if we operate with this special matrix B, it's going to bring us right back on that same vector, x bar. So x bar is, let's say, 1 over and 2 down. That's this line going through this two-dimensional plane. If we start on that line, we're going to end back up on that line. What if we look for the eigenvector associated with the second eigenvalue, which was now lambda sub 2 equal to 2? We now take and plug in minus 2 everywhere for lambda, and we're going to end up in the top having 1/2, in the bottom the same 1/2, and the off diagonals aren't changing. And we now are looking for a non-trivial vector in the null space of that B minus lambda I matrix. Again, what do you see about the rows or columns of that B minus lambda I matrix? They're dependent, aren't they? You should be able to find one is a multiple of the other. If we multiply the second column by minus 2, we get back the first column. So those are dependent again, which is good. If they weren't, then you know actually you've done an algebra mistake. You can't find eigenvectors when you found eigenvalues, and you know you've got some algebra problems. You need to have some dependency among the result so that you have a non-trivial null space. Again, if we let x1 equal to 1, then we have minus 1 plus 1/2 x sub 2 equaling 0. Now x sub 2 is equal to 2, which gives us a new eigenvector. Let me call that x hat, which is 1, 2. Again, you could have any multiple of that direction, and that will be allowing you to, when hit with B, I think that's what we were calling this matrix, you'll get back on that vector. This one now is over 1 up 2. And how is it related to our other eigenvector? Over 1 down minus 2. Those are not in the same direction, are they? Those are linearly independent, which is a nice thing. All right, let's look at another example. Yes? So now the question was, what happened to 0, 0? So I'm saying let's look at some non-trivial vectors. 0, 0 will satisfy bx equal lambda x, won't it? But that's really not giving us any non-trivial information. We know that if we're dealing with a vector space, that's always going to be in our vector space, that 0 vector, by definition of a vector space. Yes, you could have an eigenvalue wherever we started. Wow. You could have even, I mean, what you should do now is go home, maybe not between now and Wednesday. Maybe you want to focus on your exam. This won't be on exam 1. But after that, you can go home and relax and be playing with eigenvalues and eigenvectors to just relax, right? That's a relaxing thing. And you could replace -1 or -2 with a 0, and then see what you get. See what you have for an eigenvector. And it's not necessarily going to be this 0 vector. You will have a direction that corresponds to the 0 eigenvalue. Okay? So you can have a 0 eigenvalue, and if we were thinking about dynamics, then that just sort of says once you get there, that's sort of, you're stuck there in terms of a solution. If you started at that point, you're now stuck at that point. Did that answer? So I'm giving you a homework assignment for after the exam. So if you want to relax Wednesday night while I'm grading, you can play with eigenvalues and eigenvectors. Don't spend Wednesday night fretting over what you think you did or didn't do on the exam, like I used to do when I was in your shoes, okay? That's not good on your body to stress about that. It's over, okay? But prepare so that you don't have to stress after the exam if you do sufficient preparation. Let's look at another example. What about C equaling -1, 2, -2, -1? We want to see, does this have any real eigenvalues? And if you're into eigenvalues of a matrix, maybe you already know the answer to that, but you'll start to see that by inspection of that matrix. Here's our eigenvalue-eigenvector relationship. The matrix times x, the eigenvector, is equal to lambda x. We want to know, are there real x's and lambdas that satisfy this expression? Or we could write that as c minus lambda I times x equals 0, or sometimes I like to just take the negative of that or put that on the other side, and now I deal with positive values of lambda. Lambda I minus c x is equal to 0. They're equivalent. So I may say c minus lambda I or lambda I minus c. If we do lambda I minus c, then I now have lambdas on the diagonal, and I subtract the C matrix from that. So I subtract 1 from both diagonals, and I subtract 2 from the upper right-hand corner, and I add 2 to the lower right-hand corner by subtracting the C matrix. I now want to investigate whether or not I have a non-trivial real vector, x sub 1 and x sub 2, that will satisfy this equation. If we do the same algebra that we've done before, we now have lambda 1, or I'm sorry, the quantity lambda plus 1 times x1 minus 2x sub 2 equaling 0. We have, for the second row, 2x1 plus lambda plus 1 x sub 2 equal to 0. And if we play with that second equation, we can see that now x1 is equal to minus 1/2 lambda plus 1 x sub 2. That's now the relationship between x1 and x2. If we use that to eliminate x1 in our first equation, we now have minus 1/2 lambda plus 1 lambda plus 1 x sub 2 minus 2 x sub 2 is equal to 0. And we can scale that however we want. Let's now scale it by minus 2 to clean up the fraction, so that now on the left we have lambda plus 1 squared times x2 plus 4x sub 2 equals 0. Or we now have lambda plus 1 squared plus 4 x sub 2 equals 0. And like we've done before, we need to determine, is there a real lambda, a real number lambda, such that you take a number, add 1 to it and square it, add 4 to that result, and will that end up being 0? And I think it's fairly clear, phrasing it that way, that we can't find a real lambda that will allow that to happen. If we look at that, we can see that lambda plus 1 squared plus 4 is always greater than or equal to 4, which is greater than 0, no matter what we pick for a real value of lambda. And if we simply sketched that relationship, lambda plus 1 quantity squared plus 4 versus lambda, the smallest will occur at lambda equal minus 1. That parenthetical term will then be 0, but we'll still be at 4. And beyond that, or away from minus 1, we're just going up. We're never crossing the positive real, or I'm sorry, the horizontal axis with that particular expression for lambda. The quantity lambda plus 1 squared plus 4 equals 0 does not have any real roots. So where are those roots? If we look at those, we now have lambda plus 1 quantity squared plus 4 equaling 0. Applying the same technique that we did before, now we have lambda plus 1 squared is supposed to be minus 4. We now can see that lambda plus 1 is plus and minus j2. Or if we now add and or if we subtract 1 from both sides, we see that the eigenvalues, or the values lambda that cause that expression to equal 0, are no longer real, but they can be complex. But if we restricted our attention to real numbers, we have no eigenvalues for that matrix that we started with. And if we look again at what that matrix looked like, that particular matrix, if you look at it, had the real parts on the diagonal and the imaginary parts on the off diagonal. It had eigenvalues at -1, plus and minus j2. So if somebody gives you a matrix alpha, beta, minus beta alpha, you know where those roots are. They're at alpha plus and minus j beta. And that's what I was suggesting before. When I started with that matrix, maybe you already knew that that had complex roots at -1 plus and minus j2. And we've now derived that relationship for a specific example. Let's now formalize this. We've now looked at 4 different example matrices, an A1 that was diagonal, -1, -2, A sub 2, upper triangular, -1, -2 on the diagonal, a matrix B that had eigenvalues -1, -2 that wasn't clear that those were the eigenvalues initially, and here we had 1s and 2s floating around, but they weren't real, were they? We now had complex eigenvalues, -1 plus and minus j2, so we could find matrices with real coefficients that do not obtain or have real eigenvalues associated with them. Let's now jump back into the textbook and formalize this, which is really now a study of operators. For our study, now let's assume V, which is our vector space where we're playing with. We're now taking vectors from a vector space and transforming those with linear transformations, which are operators, so we come back into that same space. But now let's assume that V is always a non-zero finite dimensional vector space, FDVS over F. And that's actually, I need to switch to red. The heart of the course. This playing with operators on a finite dimensional vector space. And we may then need to try to find out or be told what F is, but once we are, then we're looking for determining the structure of these operators. That's what we're trying to do. We are now trying to understand the structure of linear operators T that now map to and from this vector space V. Now, a useful way to try to find some insight into the structure of these linear operators is to maybe separate this vector space into special representations, or putting some structure on this vector space V. A useful place to start is by considering our vector space V at as having a direct sum decomposition. What do we mean by that? That's now a question for exam number 1. What's a direct sum decomposition of a vector space, or how could we maybe write that? We could create some different subspaces, couldn't we? Maybe we have U sub 1 as a subspace, U sub 2 as another subspace, and now any vector in V is uniquely expressed in terms of vectors belonging to these subspaces, U sub 1, U sub 2, let's say up to U sub n. So let's now just write that down. That is every element in our vector space V has a unique decomposition in terms of elements of the various subspaces. And we also know that every vector space actually possesses a direct sum decomposition, or has a decomposition like this, although that decomposition might be the trivial decomposition. The trivial being V direct summed with the V0 vector case, which isn't a very exciting direct sum decomposition. Now, what the book starts talking about, now that we have these subspaces, we want to take vectors from these subspaces and operate on those by our linear map, or the linear transformation T, or this matrix representation of that A. Now, since we have split, let's say, the vector space V into non-overlapping subspaces, except for 0. All of these subspaces have the 0 vector, or they wouldn't be subspaces. Now that we have this decomposition of our vector space V, we can think of T as acting on each of the subspaces independently. And the textbook actually uses the following notation. the linear operator t, let's say, operating on a subspace U sub j for meaning or for the following: t restricted to the subspace U sub j. Now that would be nice if we were always guaranteed that that linear map would always be restricted to U sub j if we started in U sub j, but that's not always the case. Unfortunately, this isn't as helpful as we might hope, since there's no guarantee that this linear map T restricted to U sub j is an operator on that subspace U sub j. Remember our definition of operator. An operator starts with a vector space and moves us back into that vector space. That is, or i.e., it might map some vectors to other subspaces. An example. Let's consider our vector space V being all of R3. And let's just take our subspaces to be the conventional coordinates or axes, the x-axis, the y-axis, and the z-axis. Suppose U1 is the x-axis. Suppose U sub 2 is the y-axis, and U sub 3 is the z-axis. I think it's clear then that V is a direct sum decomposition, or can be written as a direct sum decomposition of those three subspaces. You can represent any vector in V as having elements or vectors belonging to those three subspaces. Since any vector in V can be written uniquely as, let's say, some V1 equal to U plus V plus W, with U belonging to U1, V belonging to U sub 2, and W belonging to U sub 3. We've now done a direct sum decomposition of V as our axes. Let's look at a particular linear map. Consider the map T operating on a 3-vector x, y, z and producing minus y, x, z. What's that doing? So if we take a point x, y, z and we now map it through this linear map, The y now becomes minus x. The x becomes y. So sort of just look at the two-dimensional plane for now. We're just rotating 90 degrees in the xy plane by this linear map. That's what this linear map is doing. Now consider what happens if we start, let's say, or look at t, this linear map restricted to u sub 1. If we now say t of 3, 0, 0, where's that point going to be mapped to? Y becomes our new x, or minus y becomes our new x becomes our new y, and z stays where it was. Did we remain in the x direction when we started on the x direction? No. So this operator does not, or t is not an operator on these subspaces that we've used to do a direct sum decomposition of our vector space V. So we have to be careful or realize that that can happen, but it's a nice concept to be thinking about relative to what we now know with operators and eigenvalues and eigenvectors. So we'll pick up at that point after exam number 1. Good luck on exam number 1.